Watch the complete playlist on the app Pions. Download the app now.
An ebonite plate, now you don't have to care about what it is because it's a dielectric. Okay, with a dielectric constant, K value here is how much? 3 and 6 millimeter thick. So thickness T is 6 millimeter. So let me write it as 6 into 10 to the power minus 3 meters is introduced between the parallel plate of a capacitor with the plate area A is equals to 2 into 10 to the power minus 2 meter square. This is the area. And the plate separation is D here is 0.01 meter. Now be very careful because this is quite important. Okay. This will clear our concept of parallel plate capacitor once again. So what we will do here is we will first draw a simple parallel plate capacitor here. The separation between them is D, between the plates, right? And area of each plate is A. Okay. Now they are saying that you are putting here a dielectric with some thickness T, correct? So this thickness is 6 millimeter, which we will take into account within a minute. So if this is T and this is D, what will be this? So D minus T, correct? Be very careful with this. Now what is D? Let's put the value. So value for D is 0.01. Okay, great. And what is T? So T is how much? 6 millimeter. So it will be 0.006, correct? So what will be this gap? That will be 0.01 minus 0.06, right? I'm just for the timing, I'm not solving, I'm just keeping it like this, right? Okay. Again, I'm repeating, we have a dielectric which is placed across this distance and the remaining space is free, empty. Where there is a dielectric, the electric field will change? Yes. How it will change? Sir, it will change as E naught upon K, where K will be the dielectric constant of that. Clear? Now, if it is K is 0 or K is infinite, okay, in that case, the electric field will vary differently. So here, there is no dielectric. So here, there will be simply electric field will be E naught because it is not there. Dielectric will polarize, and because it get polarized, the electric field changes across the dielectric, right? Great. So if these are the electric fields, we don't know what is the value of electric field, right? So don't worry about that thing. Okay. So let me take this as thickness T and let me take it as D minus T for the time being, so that at the end, when I will get a perfect relation, in that I will directly put it. Okay. So that you don't get confused, sir, we don't have electric field given in the question, and even the voltages are not given and other parameters not given. So don't worry about that thing. We will see that at the end. So in what section our dielectric is there? T, and empty space is D minus T. So in this across the ebonite plate, voltage V1 will be equals to how much? So electric E naught upon K into thickness T, right? Electric field into distance is our voltage. So across the ebonite plate, the voltage will be electric field into thickness T. Now, what is our, this is our across this one. Next is our in empty space. So V2 will be equals to electric field E naught into D minus T. Clear? Yes, because the electric field in empty space is E naught and the separation is D minus T. I hope this is clear. What will be the net potential? The total potential will be V, which is equals to V1 plus V2. If the net voltage is V1 plus V2, V1 is E naught upon K into thickness T plus E naught into D minus T. And what is the electric field between any parallel plate capacitor? Let me remind you, it is nothing but sigma by epsilon naught. What is sigma? Surface charge density, which is charge per unit area. We will substitute now that in this. So this will become, one second, this will become, let me remove this here and let me solve it here only. So this expression will become V will be equals to E naught, which is sigma upon epsilon naught K T plus sigma upon epsilon naught D minus T. And what is sigma? Just now I told you charge upon area. Charge upon area. So what will be the new capacitance? Charge upon this new voltage V. Before we write this voltage, let me take common here Q by epsilon naught A. So that here I left with T upon K plus D minus T. Now let's substitute this value. It will be Q upon, what is this? Q epsilon naught A goes up. And here we left with thickness T by K plus D minus T. Let's cancel this Q with Q. So we left with epsilon naught 8.854. 8.854 into 10 to the power minus 12. Area 2 into 10 to the power minus 2 whole divided by thickness. Thickness is 6 millimeter. K value is 3 plus D 0.01 10 to the power minus 2 minus T 6 into 10 to the power minus 3. Let's simplify it further. Okay. And over here on the left hand side. So let me just take roughly 8.854 as 9 into 10 to the power minus 12. Correct? Into and 10 to the power minus 12 and 10 to the power minus 2, 10 to the power minus 14 into 2 whole divided by 6 by 3, 2 into 10 to the power minus 3 plus 10 to the power minus 2 minus 6 into 10 to the power minus 3. Correct? Now this 2 into 10 to the power minus 3 and 6 into 10 raised to minus 3, it becomes minus 4 into 10 to the power minus 3. Let me put it here. This will be our capacitance. Okay. Now, before that, let me just take 10 to the power minus 2 common out from the denominator. So 9 to the 18 into 10 to the power minus 14 whole divided by 10 to the power minus 2 taking common. This will give me 1 minus 4 into 10 to the power minus 1, right? So that is 0.4. Let me repeat again. When you take 10 to the power minus 2 common out, you left with 1 minus 4 into 10 to the power minus 3, out of which 2 is already taken out. So 10 to the power minus 1. And 4 into 10 to the power minus 1 is 0.4. 1 minus 0.4, that is nothing but 0.6. So let's multiply here with 0.6. Let's remove this. 1 of the 10 goes up. 6 threes are. So 3, approximately 3 into 10 to the power minus 2 and 1, 3, and that will be minus 11 farad. That will be the new capacitance of this capacitor because of the dielectric.